Now, I will go through one worked out example on gantry girder. So, in last lecture we have discussed the design steps for the design of a gantry girder, and I have given an example for solution. So, I hope many of you have done. Now, we will try to check the results, means we will try to see whatever the actual results are coming, and you try to correct or modify your results, okay, if you have done something wrong. Now, the example was this, that is span of gantry girder was given as 6 meter, then it is simply supported gantry girder. Span of crane girder was 15 meter, crane capacity was 200 kilonewton, self weight of trolley, hook, electric motor, etc. is 40 kilonewton. Self weight of crane girder excluding trolley 200 kilonewton, and minimum hook approach is 1 meter, and distance between wheels are 3 meter, and self weight of rails are 0.2 kilonewton per meter. So, with this we will try to find out the section, a suitable section. So, first what we will do, we know the maximum weight of the trolley plus lifted load means W, which is weight of trolley plus lifted load, that is 40 plus load was 200 kilonewton. So, 240 kilonewton, and self weight was 200 kilonewton total. Self weight of the crane was 200 kilonewton, and crane was 15 meter span. Okay. Span length of crane was 15 meter. So, the self weight was distributed. So, total load, which is 200 kilonewton is total, right, and wheel load means the weight of trolley and lifted load, etc. was total 240 kilonewton, okay, and this is possible to get say maximum reaction at A, say R A, this is point A, this is point B. So, maximum reaction at point A if we want to get, then we have to provide the wheel load as close as possible to A, right, and we have seen that the minimum hook approach was 1 meter, minimum hook approach was given 1 meter. So, 1 meter away from the gantry we can place the load, right. So, this is the minimum to get the maximum reaction at A. So, maximum reaction at A we can find out, one is due to this total load. So, this will be R A will be total load 200 kilonewton, that is UDL load. So, 200 by 2 will be R A, and this 240 kilonewton, that will be 240 into 15 minus 1 by 15, because this is 1 meter. Okay, if we take moment about B point, then I can find out R A value, and this is coming 324 kilonewton. Okay. And this load is transferred to gantry girder through 2 wheels, and wheel base is 3 meter away. Okay. So, 2 wheel with 3 meter away it will be transferred. So, each wheel will carry 224 by 2 meter 2 kilonewton. Okay. That means 162 kilonewton. Okay. So, load on gantry girder from each wheel will be 162 kilonewton, and so factor load, factor wheel load total will be 162 into 1.5, right. So, 243 kilonewton, this is the load. So, maximum effect on the gantry girder will be obtained due to the load of 243 kilonewton in each wheel, okay, factor load. So, the wheel will be carrying a load of 243 kilonewton each at a distance of 3 meter. Okay. Now, maximum moments due to moving loads occur under a wheel when the CG of wheel load and the wheel are equidistant from the center of girder. Okay. So, that is possible if we have a position of the load in this way. Say suppose this is gantry girder, say C and D, the span of gantry girder was given 6 meter. Okay. So, this will be 3 meter, right, and then I can consider, say this is one wheel, okay, and another wheel is, say its CG is this, another wheel is here. So, this is 3 meter, right. So, this is 1.5, okay, and now it is told that the center should be equidistant from the CG of the wheel and one wheel. Okay. So, this will be 1.5 by 2 and this will be 1.5 by 2. That means, this will be 0.75 and this will be 0.75, right. This is 3 meter. Okay. And we have 243 kilonewton, 243 kilonewton. Now, if we place in such a way, then we will get the maximum bending moment. So, to get maximum bending moment, so this I can make, say this as point E, right. So, the maximum bending moment will occur in this position at E, right, something like this. So, it will be maximum bending moment, right. So, to get maximum bending moment, I have to find out the reaction at D. So, reaction at D R D I can find out if I take moment about C. So, if I take moment about C, I can find out, say 243 into this distance. This distance will be how much? This distance will be 3, total 3 minus 0.75 minus 1.5, right. So, 3 minus 0.75 minus 1.5, this will be this distance, right, plus then another is 3 plus 0.75, 243 into 3 plus 0.75, right, divide by 6. So, doing this I can find out the value of R D as 182.25 kilonewton. So, if the reaction at D is 182.25 kilonewton, then moment at point E, which is the maximum moment, that will become 182.25 into 2.25 D, because this is 3 minus 0.75. So, 2.25 D. So, this will become 410 kilonewton meter. So, maximum bending moment we can find out as this. Okay. So, once we get maximum bending moment, we can find out moment due to impact also. impact. So, due to impact additional 25% load will come into picture. So, 25% of this maximum bending moment, that is coming 102.5 kilonewton meter, right. Now, this is the bending moment because of this wheel. Now, another is the self weight of girder we can assume. So, self weight of girder, let us assume 2 kilonewton per meter, okay, because girder will also have some load, and because of that we need to calculate the moment, and dead load due to that rail was 0.2. So, total load is 2.2, dead load due to self weight and rail. So, factor load will become 2.2 into 1.5. So, 3.3 kilonewton per meter. So, moment due to dead load I can find out. Due to this dead load I can find out, say W L square by 8 maximum bending moment. So, 3.3 into 6 is the span length. So, 14.85 kilonewton, right. So, one was the maximum bending moment due to the wheel load, another is the maximum bending moment due to self weight and rail weight, right. So, this is 14.85 kilonewton. Okay. So, we can find out now total moment. So, total moment, total factor moment due to all vertical loads will be 410, we got vertical means moment due to vertical load, 102.5 is the due to impact, and 14.85 is due to self weight. Okay. So, this is coming 527.35 kilonewton meter, right. So, total factor moment due to all vertical loads are coming this, for which we need to design. Okay. So, for designing the girder, the maximum bending moment on the girder has been calculated as 527.35 kilonewton meter. Now, also we can find out maximum moment due to lateral force. Maximum moment due to lateral force. So, horizontal force transferred to rail was considered as 10% of the load, right. So, 10% of the wheel load means basically 200 was the lifted load plus trolley load etcetera was 40. So, 24 kilonewton maximum moment due to horizontal force can be calculated as 10% of the total load, that is 200 plus 40 240, right, and this load is distributed over 4 wheel. Okay. So, on each wheel load will be 24 by 4 is equal to 6 kilonewton, and factor horizontal force on each wheel will be 1.5 into 6. So, 9 kilonewton. So, lateral force on each wheel will be 9 kilonewton. Okay. And because of this lateral force on each wheel, I need to know what will be the bending moment, and which will be about y axis. So, m y we have to find out. Now, this m y is basically maximum bending moment in gantry girder, in which the position of load is same as earlier, right. So, in earlier case we can find the value m u or m z, right, which was we found earlier, right. So, here similarly we can find out the maximum bending moment about y y direction with similar proportional. Okay. So, if we make proportional, then we can find out 9 was the each wheel load, and earlier it was vertical load was 243 into maximum moment developed under 243 was 410. If you go back to earlier slide, you can see that 243 is the wheel load, and because of that moment was developed 410. So, with similar proportion I can find out the maximum bending moment about y y direction as 15.18 kilonewton meter. Right. Now, again once bending moment is over, we can find out the shear force, right, and shear force we can find out if positions are made like this, that is if one of the wheel is placed at the support, that means we can provide a load here and another load here. This is 243 and this is 243 with a distance of 3 meter, because wheel base is 3 meter. Okay. So, with this position I can find out now the maximum shear. So, if this is C and this is D, then I can find out the maximum shear V c as 243 plus 243 into 3 by 6. So, 364.5 kilonewton will be the maximum shear force coming on the support, okay, with this position. So, I need to design the gantry girder against this maximum bending moment and maximum shear force, and also I need to find out the shear force due to impact. Okay. So, vertical shear due to impact will be 25% of the earlier shear force, that is 364.5. So, this will be 91.125 kilonewton, and vertical shear due to self weight, this is impact, and due to self weight it will be W L by 2, 3.3 was the load per unit length, 9.9. Okay. So, total vertical shear I can now find out. Total vertical shear will be how much? That is, earlier we got 364.5 plus due to impact we got 91.125 plus 9.9 is the due to self weight. So, total is coming 465.52 kilonewton. Okay. So, total vertical shear we got this, for which the girder has to be designed, and lateral shear will be, lateral shear we can find out. Lateral shear will be simply, if I make proportional, that is 9 by 243 into 465.52. So, by proportioning we can find out the lateral shear, that is 17.24 kilonewton. Okay. So, we have to design because of this vertical shear and because of lateral shear, and similarly vertical means moment about z axis and about y axis. Okay. Now, we have to find out a preliminary section against this. So, preliminary section, how do we find out? To arrive a preliminary section, what we can do? First, we can find out minimum economic depth as L by 12. So, some approximate depth we can arrive as 500 millimeter. Similarly, L by 42 L by 30, that means 6000 by 40 to 6000 by 30. Okay. 6040 means 150 to 200. Okay. So, this will be the depth and this will be the width of the flange. Okay. And ZP required we can find out, right. ZP required will be m by Fy, and say 40% we can increase 1.4 times. We have seen that it can be 1.3 to 1.6 whatever we feel. To start with we can increase 40%. So, that will be m, the bending moment, maximum bending moment due to vertical load we got 527.35 kilonewton meter. Fy is 250 into 1.4, right. So, we can find out as 2953.16 into 10 cube millimeter cube. So, the required plastic section modulus ZP we can find out as this. Okay. So, we can try with ISMB 550 with ISMC 250 on compression flange at the top. Okay. So, with this we can find out the arrangement like this, say an I section, right. This overall depth is 550. This is ISMC MB 550. Okay. And top of that we have one ISMC 250. ISMC 250, right. So, with this configuration we can now check the design. That means, what we could see here, that a composite section comprising of an ISMB 550 and ISMC 250, where ISMC 250 is placed at the top of the I section in this manner, and then now I know all the relevant properties of ISMB 550, ISMB 550 from SP6, say area, depth, B, TF, DF, TF, TW. Like this I can IZ, Z, IYY, ZEZ, ZEY, and also I can find out other properties like ZPZ, right. So, R1, the root radius, all these things I can find out. Similarly, for ISMC 250 I can find out all the relevant properties. Now, once I find out all the relevant properties, now I have to find out the combined sectional properties. Okay. So, from this what I need to do, because I need to find out the design bending strength about ZZ axis, about YY axis, right. This is Y and this is Z. So, to find out, I need to find out what will be the combined area, say AC. Okay. I need to find out what is the combined moment of inertia about z, combined moment of inertia about y, I have to find out. So, this is a tedious job, means I am not going into detail of the calculation, I am just telling what we need to do, and you go through one example in the book from which you can find out. Also in the PowerPoint I will give this example. Okay. So, now you see, so first what I need to do, I need to find out what is the neutral axis depth, say neutral axis depth of the section. So, after finding out, I need to find out what is the I z of the combined section, I y of the combined section, then z of the combined section, means z means z e z, z e y of the combined section I have to find out. Similarly, the plastic section modulus. Okay. So, plastic section modulus, how to calculate, that also we have demonstrated earlier. So, using those things I have to find out. So, once I get all these properties, say z e c z, z e c y, then z p c z, z p c y, plastic section modulus of the combined section, about z z, about y y. So, all these properties we need to calculate. Once we calculate all these properties, then what we will do? We will find out the design bending strength of the combined section. Design bending strength of the combined section about z z axis, about y y axis, and that has to be more than the maximum bending moment which we have calculated earlier about z z axis and about y axis. If it is not more, then we have to increase the section size and then we have to repeat again, and if it is more, then we can go ahead. Once it is done, then we will find out the effect due to biaxial bending. That means, interaction formula has to be checked, and then again we have to see whether it is okay or not. Once it is done, then again we will go for shear. That means, the design shear strength of the section is sufficient to withstand the shear force whatever coming in the section in both the axes. That we will do. After that, we will check for crippling, buckling and fatigue, and then again we will check for deflection under working load. So, all these checks has to be done, all these checks has to be performed. If it satisfies, then the final section means finally the section can be chosen whatever we have considered. Okay. So, in this basis one can design a gantry girder. So, I hope in these 3 lectures I could give an idea about the design of a gantry girder. Basically, design of a gantry girder is nothing but design of an laterally unsupported beam under biaxial moment, and for that we need to know what are the different type of load are coming both vertically and laterally, and what is the impact load coming due to vertical load, and what is the total load, and where the wheel should be positioned so that the maximum effect can be achieved, so that maximum bending moment and maximum shear force can be calculated, against which the design will be done. Okay. So, this is all about the gantry girder. If you go through some example given in the book, then it will be much more clear, because by these 3 lectures means 1.5 hours, it is quite difficult to finish a chapter. This is basically a chapter. In most of the books you will get in a chapter form, which I have covered in beam design. Okay. Thank you.